So this afternoon we want to try to implement the regular FOSI or the forced position method for finding roots to nonlinear equations, which we have been looking at in our past lectures. As per the course computational physics, there is no point in trying to do things by hand if you can't really do them with computer. So that's what we're going to try to do today. Solutions to nonlinear equations. With forced position method. So we're going to look at the example we have in our notes. That's what the two examples which you have, and we'll try to use the examples for this particular function and see if we get the answers which we expect. I don't know about the other people. Is the link for today? Maybe I need to share the link. Just a minute. To look at the functions we looked at in the examples. So the first example we looked at was the quadratic function f of x equals to x squared minus 10x plus 23 with the forced position method starting with the interval 6.0 to 8.0. So for this, since it's a bracketing method, we need this function. So we created lambda based on this function, and when you do that, we create this function f is equals to lambda. Then how many variables does this function have? It only has one variable, which is x. Then what is the expression for this particular function? So we've got x squared minus 10 times x plus 23. So this is our lambda function. Okay. We can test if this lambda works at these particular values, at x equals to 0 and at x equals to 6.8. So we can say test, get the values, test lambda, test lambda function f of x, f of x with f of x at 6, if it works, if it gives what you expect, and f of 6.8 to see if it's going to give us the things which we expect as we have in the notes. So we're going to do the following. We're going to do f of x, which is 6, 0. So we get 1 minus 1. I think that's what we had in the notes. Then you also test the other one, f of 6 with 0. We can do them at the same time. That in this other one, 6.8. No. The other one gets overwritten. So that is 1. Then f of 6.8. That's what we get. So our lambda function is working. Okay. The next thing we need to do is we need to implement the first position method. Now there are a couple of things we need if you're going to implement the first position method, because if you look at how the first position method is implemented, I think we had, if I remember, if I can type it, begin. And equation. So the first thing we had to do was to check if there was a root between a particular interval. So, and we had this expression, I think f of a minus f of b. Then this other side you had b c dot f of a minus a c dot f of b. Now which part is not there? Which part is not there? This bit. So this is what we were following. This is how we were working out our guess root with our first position method. But before we could do this, of course, as you could see, we have to be able to work out what is the value of the function at a, what is the value of the function at b. Then this stuff we need to do, we need to check if between a and b there is a solution. But the first thing is we need to be able to work out this f of a times f of b. So when it comes to implementing the function, the first position method function, so we start with the definition, def. So this is how we tell Python that we are about to create a function. Then the name of the function is first position. That's what you have here. That's the name of the function, first position. Then the first thing is going to take is the function itself. We'll need a function. Whether you define the function as a normal function using def, or you define it as a lambda, it doesn't really matter. But we're going to need a function. Then the next thing we're also going to need is the a, the lower boundary of the interval. Then you're also going to need the upper boundary of the interval. Then here, this is for the tolerance. So I've set the tolerance where we would want to stop. We want to stop at when the value of the function at c is less, when the value of the function at c is less than 1 times 10 to the power 1 times 10 to the power 10. Okay, then we have also set ourselves the maximum number of iterations we are supposed to run this particular function. So the maximum we have set, since it's a bracketing method, we have decided to give ourselves a conservative 100 times as the maximum. If it doesn't do that, then whatever we get, whatever the answer is after 100 times, that is it. So here, this is going to be this is going to be the argument, the keyword argument for the function. This is going to be the keyword argument for the lower boundary of the interval. This is going to be the keyword argument for the upper boundary. We have set, this is for the tolerance. We have set a default value for the tolerance of 1 times 10 to the power minus 10. We have also set a maximum number of iterations, which is going to be 100. So this bit have already been set. Are we clear?
Yes, sir.
Next, we give a small description of what our function does. What is the function supposed to do? So root finding for nonlinear equations with first position method. So this is what you're going to get if you want to ask for a definition of what this particular function does. Okay, so inside our function, now we try to find out is there a solution in the interval we've been given or not? Okay, so for us to do that, we need to work out what is the value of the function at a. So the value of the function at a, we're going to keep that value as f underscore a, so which is just the value of the function at a. Then the value of the function at b. Remember, when you do this, f of a, when you do that, you get a number like this. Okay, and when you also do this for the b, you get a number like that. So we want to keep these numbers as variables, since this thing looks like function, but we want to keep them as variables. So we keep the value of the function at a in this variable, we keep the value of the function at b in this variable. After we do this, after having our values of a, the function at a in this variable and the function at b in this variable, we check if a root exists in the bracket ab. Now, we are going to be very clear here what we want to do. We are only going to do stuff if the root exists. So we check if we multiply f of a times f of b, if the product f of a times f of b is less than 0, which means if we multiply f of a times f of b, if we get a number which is negative, which is going to be less than 0, which will make this true, then we'll print out the root found in this particular interval. So basically, this is supposed to just print out, say, the root is found in interval AB. Then we'll start doing all the things we need to do. However, if the product f of a times f of b is greater than 0, then, so this whole thing which is here will only happen, all this up to this point, all this will only happen if all these things I've highlighted from there, all this stuff which we're going to go through up to this point where I've highlighted, this stuff is only going to happen if f of a times f of b gives us a product which is negative, which is less than 0. Otherwise, if we get a product which is positive, then we are going to print out the message else. That's why the else comes in here. Else, we're going to print out a message to say root not found in interval AB. Are we clear? And the whole thing just comes to an end. If you give an interval in which the multiplication of f of a times f of b gives us a positive number, which means that there is no root in that particular interval, then there's nothing else to do. We only want to do things if there is a root in between a and b, which is what we have here. So if f of a times f of b is less than 0, then we want to start doing things. So the first thing we want to do is we probably want to tell you, okay, fine. Maybe, I don't know if we should say anything. I don't know, because it doesn't come out nice. Because I've run this, it doesn't come out nice. But I think we could, instead of just saying there is a root, I think we should just give you what the root is. Otherwise, telling you there is a root in this particular interval, then proceeding to give you what the root is doesn't really make sense. Okay, so I think what you're going to do is we'll not print this statement, root found or whatever it is, we'll just give you what the root is. But if there is no root in that particular interval, then we print out this statement. Say root not found in interval AB. That's the statement you're going to print out here. Okay, so if this statement is true here, so I think I should remove this. Then we can start our, remember we started with k equals to 1, k equals to 2, k equals to 3, k equals to 4, like that. That step of doing k equals to 1, k equals to 2, k equals to 3, k equals to 4, that is us repeating a particular step a certain number of times. So that repetition, a repetition which you can carry out a certain definite number of times, we can implement that using a for loop. So if we want to start with, we have got our maximum number of iterations which we want to do, that is going to be 100. So we can use this function in a for loop. So we can say for k in range. So in this case, range, we start from 1, then we want to end with max iter. So this whole thing is going to produce a list of numbers from 1 up to max, from 1 up to 100 in steps of 1. So we're going to start. There is nowhere else where we're using the k. We're just using the k for the number of iterations. So the next thing we're going to do after setting up our for loop, since we have to repeat this calculation a certain number of times with a maximum of 100, the first thing we're going to do is we want to carry out a calculation for our guess root c using this expression. C is equals to b f of a minus a f of b divided by f of a times f of b. Now remember, the value of the function at a and the value of the function at b are being stored as fa, f dash a, and f dash b. So what we end up having, we can straight away calculate what our c is going to be. So our c is going to be b times f dash a, f hyphen a underscore a minus a times f of b, then divided by f of a minus f of b. So this is going to give us our value of c. Since we know what a is, we know what a is, we know what b is, we have just worked out f of a here, we've just worked out f of b here. So if we've worked out f of a and f of b, then we can work out what our c is. Is that clear?
Yes, sir.
After working out what our c is, the next thing we need to work out is the value of the function at c. What is the function at c? So we work out this bit, f of c, which is what we're going to store as fc. Now, after working out f of c, which is what we're going to store as fc, the next thing we do is we check if fc, the value of the function at c, is equals to 0. If fc is equals to 0, then we stop. We stop because we have found what the answer is. Are we clear? So here we check, is the function, the value of the function at c equals to 0. So if fc is equals to 0, then we stop. So here we stop and exit the loop. So here we stop and exit the loop. Stop and exit for loop. We stop and exit the for loop. Stop and exit for loop. That is if f of c is going to be equals to 0. But remember what these things are. These things are approximation methods. So it's not likely that fc is going to be equals to 0 unless we change our tolerance to something which is very, very small. So that is practical. It's going to be practically equals to 0. But we put it as a precaution. You never know how these things work. Okay? So if fc turns out to be equals to 0, when you work out, you calculate the value of c, then fc turns out to be equals to 0. In such a case, then you just stop. So if fc is equals to 0, then you break. You stop and exit the for loop. Then you're done. Are we clear? After exiting the for loop, you give us what the value of c is. You're also going to give us what the value of your function is. So here, this from here, this is part of the for loop up to here. This is what the for loop is doing. This bit here is outside the for loop. So if your value of the function at c is equals to 0, then you come out of the for loop. Then you give us your value. What is the value of c you have found? What is the value of fc? And how many iterations has this thing run for? So you give me what is your C, what is the value of the function at C, and how many times did it run. So you give me this. So return, say return tuple, return a tuple, return a tuple, return a tuple of C, FC, and K. K being the number of iterations. So this is what you have here. Is that clear? Are we clear? Here, are we clear with this? To say if FC is equals to 0, then we have found the answer. There is no need to do anything anymore. Is it clear?
Yes, it's clear.
Okay, but like I've said, that is not going to be likely to happen. Okay, so we are going to proceed. The next thing we're going to do is we're going to do the following. We are going to check the products FA times FC. So we're going to multiply FA times FC. When you multiply FA times FC, we're going to check if FA times FC is greater than 0. If the product FA times FC is greater than 0, it means that this product is positive. If it's positive, it means that between A and C, there is no root. So if between A and C there is no root, then we are going to squeeze from A. So our C is going to become A, and our f of C is going to become f of A. So we'll be squeezing from A. Are we clear?
Yes, sir, it's clear.
So there are three conditions. One, FC, or you could say f of A. You could do the following. F of A, instead of writing FC, you can say f of A, FA times FC equals to 0. That's the same thing. If FA times FC is equals to 0, then you break. But if FA times FC is greater than 0, then you do this. Else, the only other thing which is going to be there is that FA times FC is less than 0, meaning that between FA and FC there is a root. So if there is a root, then you're going to squeeze from B. So your C is going to become B, and your f of C is going to become f of B. Are we clear? If this product f of A times f of C, because we have to work out a C, then you find out what the value of the function is at C. So if we work out this thing, f of A times f of C, if f of A times f of C is equals to 0, then we stop. But if this product f of A times f of C is positive, it means that between A and C there is no root. So you squeeze from A. So your C becomes A, your f of C becomes f of A. Otherwise, the only other option is if it's not equal, if it's greater than, it means that that's where the else comes in. It should be less than 0, meaning that between A and C there's a solution. If between A and C there's a solution, then you squeeze from B. You start squeezing from B. So your C is going to become your B, and your f of C is going to become your f of B. Are we clear?
Yes, sir, it's clear.
Okay. The other condition under which you are going to come out of the for loop is if the value of the function at C is less than the tolerance you have set. If the value of the function at C is less than this, if the value of the function at C is less than this, then you also want to come out of the for loop. So you have set two conditions to come out of the for loop. The first condition is if this f of a times f of c is equals to 0. You want to come out of the for loop because we have found what the answer is supposed to be. Since you're multiplying this bit, or we can leave it. I don't know if it makes sense, but we can leave it like where it is. So if the value of the function at c is equals to 0, we want you to come out of the for loop. Then also the other condition is if the value of the function, the absolute value, so the value of the function can be positive or can be negative, but we don't really care whether it's positive or negative. That's why we're using the absolute value here. We're using this function abs. If the absolute value of the function is less than the tolerance you have set, we also want it to come out of the loop. After we come out of the loop, then we want to look at what value of c we have, and also what is the value of c and how many iterations we've done. So when you do that, so this thing will repeat itself. Since it's a for loop, it's only going to stop either when we reach the maximum number of iterations, or when this happens. When this happens, we want it to stop. We also want it to stop when this happens, when this condition is met here, where the value of the function is less than the tolerance, then we want it to stop. Then after it stops, then we want to get a tuple, or what is the value of c, what is the value of the function at c, and how many iterations it ran. Are we clear? Are we clear?
Yes, sir, it's clear.
Okay, so we run this so that our function is updated. So now with our problem, so we call the force position method. So with what we have here, we have already defined the lambda for this function. Our a is 6, our b is 6.8, and the function f has already been defined. We have defined it. So we call the force position method. Our force position, the function is going to be set to f. Our a is going to be set to 6. 6. Our b is going to be set to 6.8. Then when you run that, this is what we get. So remember, we are getting a tuple. We're getting this tuple because we are returning the value of c, then the value of the function, then the number of iterations. So if we want to get things separately, we can say the root, the value, f_val, function value, and iteration. You can do this. So get that, then you can display what your root is, then you can display what the function value is, then you can get the number of iterations. There. You notice that this is consistent with the answer we found. In our notes, if you check your notes, you find that that's very consistent. display. Display the root. Any questions? Display the number of iterations, 12. This bit here, which we have done here, this is what is called tuple unpacking. How you unpack a tuple. That's stuff we did when you're looking at tuples last year. So unpack the result. Unpacking the tuple. The result returned as a tuple. Okay, is that clear? If we try to see if this thing works or not, we try to give a bracket which is different, which does not have a solution. So in this case, we change. We try to give, instead of 6, we say, okay, let's say 4.5 to 5.2. We do that. Then we try to run this function. Force position, func f a is 4.5, then our b is 5.2. We do that, then we run it. We just stored root not found in this interval 4.5 and 5.2. That's all. That's all it's supposed to do. If there is no, when you give it these parameters, you give it a function, you give it the lower bound of the interval, you give it the upper bound of the interval, then it checks. Then it finds out that f of a times f of b is greater, it's positive. Then it's just supposed to tell you no root found. So the function should be able to check. If there is a root, if there is no root, it tells you in this particular interval there is no root. Okay? Otherwise, if there is a root, then it should start doing things. Start going through this process. If there is a root between A and B, then it should start this process. It starts this process until this process comes to an end. Either because f of c is equal to 0, or because, most likely because this bit here, the absolute value of f of c is less than the tolerance. Then you should return c, you should return f of c, you should return k. Are we clear?
Yes, sir.
We have another example in our notes. Let me just look it up. Okay. Example number 2. In example number 2, our equation is cos x minus x plus 1. Cos x minus x plus 1 equals to 0 in the interval 0.8 and 1.6. 0.8 and 1.6. Okay, so we're going to create a lambda function for this guy. But before we do that, we need to import a function. So we're going to say since there's cosine there, so you're going to say from math module import cosine function. So that's the first thing you're going to do. We need to use a cosine function. So say from math import cos. Then you're going to create this cos x plus 1. Sorry. Say f is equal to lambda. How many variables x? Then the expression is cos x minus x plus 1. So that is our function, the function which we're going to give. We can check if everything is working properly by doing some small things. We can test our lambda. At 8 and 1.6, if it's doing things as we expected, f of that's what we get. Then f of 1.6, we get a negative thing, as was similar in our notes. So the first bit is positive, the other bit is negative. So with this information, we can call our function. We can call our force position function. Call our force position. With keywords func func set to f, a set to 0.8, and b set to 1.6. There. So say force position func f b set to 0.8, b set to 1.6. Remember, we don't have to provide any information about the tolerance and the maximum number of iterations because that stuff has already been provided. If we do that, this is what we get. We get our C as 1.2, 1.283428781737 and this is the value of the function, that particular thing. Then this thing only runs 6 times. Exactly. You can do an unpacking. You can say say root f value iteration. You can do that, end up with that. Then you can display your root, you can display your other things. So in this case, you wrote just that function value, f value is that, of course, the number of iterations. Iterations is that. Are we clear? So we've done our 2 examples. We have a program which works, so you can use that if you want to implement force position. Are we clear?
Yes, sir, we're clear.
Any questions? So you have got something you can use even as you do your assignment to check if things are correct or not. You have a custom, we have a code we have come up with, we have built, which we can use to check if the solution which we have with force position is giving us things which make sense or not. Alright, so unless there are any questions, we have come to the end of this chapter 1. Next week we're going to start looking at a method we can use to work out systems of linear equations and also systems of nonlinear equations. The same method can be used to work out systems of linear equations and also systems of nonlinear equations, which is what's referred to as the Gauss-Seidel method. So instead of what we did last time, where we're doing Gauss elimination and also we're trying to do LU decomposition, you don't have to do that anymore. You can use another method, an iterative method, which is referred to as the Gauss-Seidel method, and that's what we are going to look at starting next week. Okay, unless people got questions. Of course, I will not be doing a lot of teaching of Python, since if you want to refresh on your Python, you can go to my YouTube page. You should be able to find content there, which we were doing this year. We were able to record a lot of videos on the Python bit, so if you need revision, you can go on my YouTube page. You'll find a lot of videos. Okay, so if there's nothing else, we are going to end here. See you next week, or see you on Friday, hopefully.
Thank you, sir.
Cheers.